Are y'all ready?
Yeah, I think I'm good.
Are y'all ready? Sure.
I can't hear you.
Welcome to Mechanical Info Day. I've probably seen all of you on Intro Day. If I haven't, that's all right. But yeah, anyway, we're going to go into some more depth into what we went over on Intro Day, along with some other goodies. So overview, what are we going to cover today? Well, first off, what is mechanical? I know we've already addressed this question in Intro Day. We're going to go like a little more depth into it. And then next up, we're going to have like a kind of a lecture thing for FRC specific design, led by.
Project yourself.
We're going to have a FRC specific design section. It's kind of a lecture thing that's going to be held by our lovely other Max. Would you like to introduce yourselves?
I'm Sharon.
I'm Ben. I'm Alex.
I'm Justin. And then after that, we're going to break down our schedule. You'll see how we operate things in build season, off season, and all that good stuff. And then mechanical resources, that's our next thing. And at the very end, we'll have an activity for you all. So get ready for that. So anyway, what is mechanical? Well, we've already gone over this, but anyway, just to reiterate, we are the department that handles design, fabrication, and assembly of a competition season robot. And basically, we follow these three things, these phases, for basically any project that we pursue. First off is design. This happens before any fabrication happens, and we do this by CADing. Do any of you know what CAD is? What is CAD? CAD is computer-aided design. It is basically 3D modeling, and we go into CAD to 3D model our competition robot before we actually fabricate it. And this is to make sure that nothing interferes and all of your things that you think your robot's going to be works. And then so fabrication is next, or after our design gets reviewed and we make all of the corrections necessary, we go into fabrication. This is where we utilize all of the machines you see here in this lovely workshop to make that robot, to make the components for that robot. And then lastly, we assemble the robot. It's pretty self-explanatory. And then next up, we have a video from Grant Imahara. If you watch Mythbusters, you'll know who that is. He is actually an FRC mentor for I don't know which team. But anyway, great guy. Oh, I didn't think this through. There's sound.
Jesus Christ, Justin.
Can you hear that?
Hi there, my name is Grant Imahara, and I'm one of the hosts of Discovery Channel's Mythbusters. I'm also an electrical engineer, a robot builder, and, oh yes, a former FIRST mentor. I'm here to talk to you today about the importance of design. Look, I know what the first season's like. It's intense. Everyone wants more time, right? Well, you don't get more time. No, you don't. But through design, you can make better use of the time that you have to be more efficient and get more done. Now, I know it's tempting to just grab a piece of aluminum and start building the first thing that pops in your head. I know, I have. But this really only works for very simple challenges. And as we all know, FIRST is anything but simple. FIRST robots are, by nature, complex machines. In order to build them with the capabilities that you want, given the time that you have, requires careful thinking. The design process is your roadmap through this minefield. Seeing that journey and understanding the process of design is what this video is all about. Now you're saying, I already know all this, Grant. What's the difference? Well, the difference I'm suggesting is that you pay a little more attention to the very early stages of your design process. Now you're probably thinking, whoa, we do design. We draw it on a piece of paper or on a whiteboard and then we build it. Well, before charging forward to making parts, just take a little time to make a study model. It can be in the computer using CAD, computer-aided design, or it can be popsicle sticks and paper towel tubes. It doesn't matter what you use, as long as it helps you work out the problems. Because, let's face it, making a part over and over and over again is not only frustrating, but also very time-consuming. You know what I mean. You make a part, you test it, take the assembly apart, put it on the drill press, drill a new hole just a little bit further, put it back together, rinse and repeat. In the end, you've got something that looks like a piece of Swiss cheese rather than a robot part. By using a model to test your ideas before making parts, you'll save materials and time. What? You don't believe me? It's already been done by many teams. I'll show you. Within First, there are hundreds of instances of great design, but today we're going to focus on one notable example of excellent robot design. Team 111, Wildstang, and their lifting arm. This is their design story. Step 1, define. Understanding the problem. The challenge was to pick up an inner tube from the floor and lift it up 8 feet, using a mechanism that was limited to an initial height of only 5 feet. Their design needed to be strong, lightweight, and controllable. These requirements and constraints defined the problem that they had to solve. The team started with a review of the required geometry, called the Kinematic Analysis. Basically, how small did the robot have to be to begin with, how long the arm had to extend, and the types of movements required. They used hand sketches to quickly identify the critical dimensions. Based on this analysis, they established that 2 linkages connected by rotational joints could accomplish this task. Step 2, ideate. Brainstorm. As a result of their discussions and brainstorming sessions, the team decided to model their robot arm on a human arm. The robot arm would rotate along 2 axes at its shoulder and along a single axis at its elbow. They decided to make each aspect of the arm analogous to a human's, with linkages as bones and power sources as muscles. Next, they had to build what they imagined. Step 3, create. Building. Team Wildstang used the CAD approach, building their arm in the virtual sense, in the computer. But as I mentioned, you can use whatever you want to make your models. They divided the arm into its major components, the shoulder, the upper arm, and the forearm/gripping system, and assigned each part to a different sub-team. These sub-teams worked independently to model their designs using CAD, and then put all the models together for testing. Early testing revealed that the original gripping system could hold a tube, which is good, but the tube rotated if you moved the arm too quickly, which is bad. Within the computer, they then easily moved around the pivot points until the arm had better range of motion and a stronger grip. The whole time they kept plugging away at the models to improve performance. See, they did all their testing in CAD and solved the problem virtually before any of the parts were actually made. Their computer corrections solved the real-world problems. Now that their virtual design was working great in the computer, it was time to make the parts, put the robot together. Step 4, solve. Manufacturing. Wildstang's CAD models not only helped them test the arm, but also served as detailed blueprints for fabricating the actual arm components. Each bearing, mounting hole, and attached part was precisely specified in the CAD model. This allowed them to make the final parts in one pass, saving materials and, more importantly, saving time. The result? Wildstang's arm had a full range of motion, was easy to control, and was strong. A phenomenal success. They used CAD to streamline their design process to keep them moving forward toward their goal. To review, make a model, work out your ideas, then make your parts. And like Team Wildstang, you can follow the same design path to efficiently create an elegant solution. And that, my friends, is what great design is all about. Or you can struggle through it the hard way. It's up to you. Either way, we better get started. Clock's ticking.
Can I jump in here for a sec?
Sure.
Okay, hi, I'm Chris Lowe. I'm one of your mentors. I'm a mechanical engineer. Team 111 is from Arlington Heights, Illinois. So in case you're a little unnerved by how well they're doing, they have 6 high schools, the same size as this school, that they pull from. One team, 6 high schools, and if you wanted to be on the team right now, your application was due last February. They only take seniors, they only take like 20% of the people who apply, and they've got like 1,000 mentors, so don't panic.
No pressure.
Don't panic.
No pressure.
Okay, thank you, Grant. Next, we're going to head into general FRC design, led by our lovely Max here. So what we've essentially done is we've split up the competition robot into 3 major subsections. the drivetrain, the intake, and manipulator, and here we go.
All right, so the drivetrain is the basic base of the robot. This, interesting, slow is smooth is fast, except with drivetrains, which, yeah, your fast drivetrains might be kind of rough. All right, so the way the drivetrain works is it's obviously just straight up the wheels of the robot. How they work, how you manipulate them. It allows you to move around, reach objectives, everything basic movement requires, so your robot doesn't, just sit there after the start and do absolutely nothing. It's also structurally the base of the entire robot, and the way you can design it can vary greatly to accomplish different tasks and focus on different focuses of your robot. So there's a few main types of drivetrain. The first that a lot of people do is the tank drivetrain. It's incredibly simple, and it generally is consisted of straight normal wheels, 3 or 2 to a side, and each side can be controlled individually to allow you to turn. They generally have pretty high torque, and they have full range of movement forward and backwards, but they can't move left and right on a dime. They have to actually rotate and then move forward, which is not necessarily a constraint, but depending on what your robot needs to do, it can be useful or detrimental. Also, you can be pinned from the side because you can't actually, go in that direction. You have to turn, and you can be stopped from turning by another robot. Then we've got Omni/Mecanum wheels. Mecanum are kind of a joke, but they can be used to great effectiveness. Omni wheels are wheels that allow people to not only move forward, but also sideways. So that gives you complete omnidirectional movement. However, it generally sacrifices torque, and you don't have as much traction because the ability to roll in every direction means you can be knocked around in every direction. But if you need to cut corners really fast or optimize your ability to get somewhere, Omni wheels help with steering and directional mobility. Thank you. And then there's the Swerve Drive, the alleged and mythical Swerve Drive, an incredibly complicated mechanism that allows the wheels themselves to rotate to any direction that you want them to face. It gives you the full direction of movement that an Omni wheel drive gives you without losing any traction because it has the wheels facing in the direction like a tank drive. However, being incredibly large and complicated, they are very fragile, very difficult to construct, take up a lot of a robot's weight, and have to be done in very particular ways to actually be effective. And in many situations, they're not really what you want to do, but they're there, and a few teams do them to decent effectiveness. For your drivetrain, you avoid high maintenance designs. Your drivetrain needs to be able to function repeatedly over and over and take a beating because it's what's going to be smashed into walls, game components, and sometimes other robots. It's also at the very base of your robot, so it needs to be a very strongly constructed piece. It holds up everything in the literal sense that everything is built on top of it. So everything is quite literally relying on it. It needs to hold up, and if you're repairing your drivetrain all the time, you're having issues, which means you can limit your ability to do anything in the game because it's how you move. If you can't move, you're basically dead in the water.
So the intake, it is what grabs game components. And actually, you want it, pretty much. Each year, there's at least one game element that will require you to grab and or manipulate. This happens every year without doubt. This happens. As you can see, intakes can consist of balls, in which case we have a couple of rollers that will suck the ball up by rolling those rollers at high speeds that will create an upward pull. And there are also other intakes that have to pick up squares. This can consist of a flipper, you just flip it inside of something, or in this case, a gear, which was not fun to build. In this case, you just treat it like a square. You just have it on the ground, and then you'd have two rollers similar to the ones you would see in balls, just suck it, and then use its torque to hold onto it, where the manipulator could then move around and stuff. Intake good practices. If you touch it, you own it. No one can take it out of you for obvious reasons. But always aim for an active captive system. That means that once you have it, you won't let go of it. Basically, you always are putting in energy to make sure it stays where it is. You don't just plop it on top of the robot and hope for the best. And
moves the object. Well, so the intake intakes it, and then the manipulator moves it around and places it wherever you want it to go. They get the game elements from point A to point B. So for example, since there are two different types of manipulators, there's types for the ball, and these manipulators are usually made with wheels, or they have rollers or something, and they pick up the ball and they are able to shoot it, or they're able to place it somewhere. And the shooters are usually pretty hard to build. For example, that one over there, they use wheels to shoot the ball out into the goal. The second type of manipulator is for the non-ball objects. In this case, it can be cubes like we had last season, or gears, or toads, or
Trash cans.
Yes, trash cans. And these manipulators are usually elevators or arms, or in the case of 118, they have an intake that picks up the cube and then has a separate manipulator to grab the cube and move it. And I'm not sure what team it is over there, but the one on the very left, it has the intake integrated with the manipulator, so you don't have to pick up the object twice. Same with the intake. If you love it, don't let it go. You don't want to drop the object. And you want a really good design for your manipulator, because if it breaks, you can't move the object around. It's harder to get points. And you want it to be as fast as possible without making it bad. You also want it to be consistent so that you can get the object where you want it to go consistently without worrying whether or not is it going to make it, is it not going to make it.
Thank you. Next, we're going to break down our schedule for this season. When does mechanical meet and what do we do during these time periods? First, I'm going to talk about build season. Excuse me. This is a period of 6 weeks where all teams are given a challenge. And this is marked by the FRC kickoff event, which is 8 a.m. on January 5th. This is where the FRC Game Design Committee releases the game to all of the FRC teams in the world. And this is a worldwide event, and we come here on the Saturday morning after winter break, and we all come together and decide how we want to approach this game. And then after that officially starts our 6-week build season, which is where we do things like design, fabricate, and assemble the robot, obviously. And then build stop is on February 19th at 8:59 p.m. The robot gets bagged, and you literally cannot touch it until the competition starts. And so off season, which is the period we're in right now, this is now until build season starts, obviously. Our workshop loud days are Wednesdays, Thursdays, and Fridays. This is when mechanical is going to meet. And the reason why they're called loud days is because we have a lot of noisy machines in here, and the admin building's right next to us, and we want to give them a break from all of our loud machining. And, both. And when build season comes around, obviously we can't avoid machining, so we come in every day of the week, and we have to use the machines on every day. And next is, there will be workshops or seminar type of thing held at SDA, hosted by Team 2012. Oops. 2102, my apologies. Team Paradox. They will be held on Mondays from 5:15 to 7:15, starting on September 24th. And these are seminars that range in topics from things like physics, FRC specific design, and if you're interested in controls, actually, there's one on wiring. And I know I haven't touched on fabrication much, but the machine training for these specific machines, they will start immediately after Info Week. So what that means for you guys is I want you to get your online general safety training done as soon as freaking possible, because you will need those safety glasses to be able to interact with the machines. You guys have all heard of what that is, correct?
How do we know if we passed the quiz or not?
It's 80% or above, I believe.
You
No,
can
but I mean, I
see
didn't get the
You can
results.
Oh.
Slack me,
They
you can
can't see the
email me,
results, right.
I know. I wish it would let you know, but it doesn't, so.
So yeah, pass the quiz, get that waiver signed, all that good stuff. We will begin machine training immediately. And if you don't, that's okay. We will run some machine training again for those that missed the initial wave. Yeah, this is just going into more depth about the SDA workshops. These will be held at San Diego Academy. Oh yeah, I just fixed the numbers here. Nice. Mondays, 5:15 to 7:15. First one is going to start on September 24th. There are 5 spots reserved for each school coming. What that means is 5 people can go, and then we can start adding additional people that want to go. So I think I might do a kind of first come, first serve kind of thing. So if you want to join or are interested, definitely come talk to me, and we'll get that sorted out. These are the topics. They were in this picture over here. I don't know if you're able to see them very well though. So anyways, these are the specific topics that they will be going over. On September 24th, gravity gets me down, but pneumatics fills me up. This will be an introduction to physics and rotational forces and pneumatics. If you already have experience in physics, you don't really need to attend this one. The next one is Tony Stark's Basic Physics on October 2nd.
More physics.
More physics, physics 2 basically. And it also covers some of electricity and motor selection type stuff. And then the next one, manipulator design specifically the intake, shooters, arms, and elevators. This one is actually hosted by our very own Garrison Price, our mechanical mentor. So definitely be interested in that one. And then the next one, it kind of splits up into 2. There will be one workshop on October 15th for strategy or leadership. And then a second one for geared towards mechanical for COTS, off-the-shelf items, kit parts, common hardware. I doubt any of you will need to attend the first one of those 2. And then the next one is if you are interested in the controls part of this team, this will actually be for you. This is learning about the FRC control system and how to wire the robot to survive a competition.
Actually, the guy who's running it it's everything. It's a Robo Rio, it's all the controls, how do you wire it up, how do you solder, make sure you remind the mechanicals that there are wires and don't leave that out of your CAD design, that kind of thing.
And then the last one, which will be on November 5th, is learning about how to use iterative prototyping to perfect a design. So these are the workshops. They will be every week, Mondays, starting September 24th. If you are interested, you can come talk to me to get signed up and all that good stuff. Remember, we have 5 spots reserved, but we can add additional people to those that are interested. Anyways, next up, mechanical resources. So I've been so nice as to provide you guys with some resources. Currently, there is only a design and CAD kind of resources thing out there. I am in the works, or I am working on a fabrication resource. Let's take a look. So I made this so that if you are in the process of designing and say you happen to forget how to select a motor for a particular application, you can come here for reference for, yeah. Even I need to come here sometimes because I forget things like basic physics and how to select a motor. And then anyways, this goes into, some of these documents go into how we operate specifically on this team, such as the CAD part assembly nomenclature reference. This goes into how we name our files and why we do that. And then the other ones, things like physics reference, the gearing, gearbox. This is really for you guys. This goes over basic stuff like gear nomenclature, things like pitch diameter, diametric pitch. things that are really important to get to know gears and how to use them. And then this physics reference, which, yes, you will be using physics when you design. Obviously, we use things like motors and pneumatics on this FRC team, and motors generate rotational motion, and you can turn that into things like linear motion, or you can just straight up use that motor and make an arm. And so you'll be dealing with torque in that instance of using an arm. And in this physics reference, we basically go over things like how to actually apply that physics to an FRC kind of design situation. And then motors calculation is basically how to pick a motor. We actually have like, I don't know, 5 types of motors. Over the course of this build season, you'll pretty much get acquainted with what these motors specialize in and why we use one over the other. But this one basically goes into how you can select a motor and the differences between them. And you will start reading things like motor curves, lovely motor curves. These things tell you how, like, at a specific torque, you know, how much current are you drawing or how much speed are you getting out of it. And there are ways you can just straight up take a motor and say, oh, this motor produces this much torque. Let's stick it here. It produces enough torque for this application. On the other hand, you can use these motor curves, read them, and actually optimize it for your use. And that's what we did this year with the elevator. We actually optimized 2 sims that are running at basically peak performance. We're getting the most out of the speed and the torque. And yeah. So there's other stuff on here. Things like rotational motion references. This goes over things like pulleys and sprockets. And I go into like terminology for each of them. And if you need to, sometimes I forget how to calculate center distances for sprockets. But we actually have a lovely sprocket calculator for the center distances, so you don't need to do it yourself. And yeah, these basically go into calculations. So when you're designing, and there will be many calculations involved, and these references will kind of guide you and help you in that in the case that you forget any of them. And this one here specifically goes into how we actually dimension gears in SolidWorks, and you can see that it's visualized. And I sort of go into the math behind it, if you really wanted to know. Anyways, back into the last portion is our activity. So for 10 minutes, I will have you guys basically come up with a single mechanism. You don't need to come up with a robot, an entire robot. I'll be splitting you up into 3 groups. Yeah, I think that works. 3 groups, and you will discuss among yourselves how to launch this 10-inch boulder, which is basically just a dodgeball. So I will see if I can get you guys pencil and paper, but you'll discuss among yourselves, and after 10 minutes we'll regroup and kind of unpack what we've come up with. Do you have any questions? No? Anyways, we'll split you up by rows, I guess. First 3 rows are one group. The next 2 are another group, and you last 2 groups, or 2 rows, are the last group. Good? Any questions about your task or activity? First 3 rows, you guys are group number 1. The next 2 rows are group number 2. And then you last 2 rows are the 3rd group.